All right, let's have a look at concave mirror image location. And what I'll do is I'll draw a center line here. We'll put the mirror down this end because we're going to find out that with the concave mirror, we can have it there. So this is, if we had a focal length of, let me just get this straight. If we had a focal length of, I'll put it about 5 there. So we've got an F of 5 centimeters, a C there. Then I'm going to just start by having an object that's out beyond C. So I've made the object, let's make it 3 centimeters tall. There. So the 3 rules we talked about, we draw a, should I use a different pen for this? Maybe I can. I'm just thinking what color. Let's just, you might be able to see red. You see, just if I use a normal pen. No, that's a bit crappy, isn't it? Try this one. So that's my first ray. It's gone through parallel to the mirror, and we all just know that that's going to go through the focal point like that. Nice. Always draw the little arrows on it so we know what we're looking at. Now, we also said one that goes through the focal point is going to go parallel. I'll try and get that reasonably parallel. And boom, we've already got the location of our image. We also said if it bounces off the middle of the mirror, third rule, that it will do an equal angle, which is that. And we end up with our image right there. So that's our object. That's our image. That's a real image. And you can see it's smaller. So it's real, it's diminished, and what else do we need to know about it? Upside down, inverted. All right, so from a work things out point of view, if this one was, I don't know, 124 millimeters, so DO equals 124 millimeters. The focal length on my mirror is equal to 50 millimeters. I could then use Descartes' formula, 1 over F equals 1 over D naught, 124, plus 1 over DI. Now, if you solve that, you need to make sure F is positive because this is a converging lens. And remember, sorry, this is a concave mirror. F is positive. And what you'll find is you will end up calculating, and it should come out to close to about 85 millimeters when you actually calculate that. So that should all work out. So real image in that location. But the thing about this mirror here, as we move that ray in a bit closer, we'll find it does a few other things. So let's do that. We will do exactly the same setup. Concave mirror, boom, boom. Let's put our focal point in, and let's put our C in, there, there. But this time I just want to put my, I think it was a 4 centimeter object, and I want to just put it in between C and F and see what happens. And what you'll see, and this is, you should be sort of expecting it, that's F, that's C. What we're going to find is we're going to get a difference in our image distance, and that's going to create something that we need to see. So there's our rays, one through the focal point. We did the parallel one going through the focal point. Now we'll do the focal point going parallel. Whoops, right down here, isn't it? Look at that thing. So it goes all the way down to there. We haven't even got enough mirror. And then it carries on across here parallel, right? So we need to extend this ray further. We didn't have it going far enough. And boom, we got it. I could do the other ray if I wanted, but I don't need to. I've got this really big image. So when we brought the object in closer, we got this really magnified image. So in this one, we had a diminished image when it was out past C. Now we've brought the object in between C and F. We have an enlarged image, and you would find if you went to C, the image would be the same size. So, but notice our formula, 1 over F equals 1 over di plus 1 over d naught. If this gets smaller, all right, then, so we've got do getting smaller, then this whole ratio gets a bit bigger. This needs to get a lot bigger to make it smaller, to make it all equal 1 over F. But the other thing to remember is H equals M equals di over do. So as the di got bigger, the magnification got bigger. So those are the things to notice there. But we've actually got a third situation, which is where we can bring the mirror in, not the mirror, the object, in even closer, where we've got, let's have a look here. Oh, making a mistake here. And I'll tell you why I'm making a mistake, because what we're planning to do is bring the object even closer than the focal point, and we're going to get a virtual image. So we want to draw that one with the mirror a little bit more like this. So we've still got the concave, we've still got the 5 centimeter focal point, but this time we're going to put our object, I'll make it a smaller object, but we'll put it about here. We'll make it a 2 centimeter object about there. So it's in between the focal point and the mirror. Now you can see stuff's going to be a little bit different this time, and the same things apply, but you'll see what happens. When I draw a ray that goes through the focal point, there is only one focal point. So it's got to go from the focal point, tip of the object, and then it's going to go parallel. So it goes like this. What sort of, it doesn't look like it's going to create an image at all, right? How are they going to intersect? So we've got some issues. But let's just keep with the plan. Let's draw one that goes through, it goes parallel. And we said those ones then go through the focal point. That's all very nice. So there we go. We got that. Now we know that when you're looking at a mirror and rays come off, you see them as if they come from behind the mirror. So there's the virtual part of that ray. And same thing for this one. So what you end up getting is a virtual image behind the mirror, right there. So that becomes our image. Object, image. Image is upright. It is magnified. And it is virtual. We can see that from our diagram, right? We can see it from our diagram, and we can also see it from our formula. 1 over F equals 1 over dO plus 1 over d naught. F is still positive because this is a concave mirror. But when we made that object distance really small, this got really big, okay? It got bigger than what we were going to do here. So this whole thing became negative. So we end up with a negative di, and that means it's virtual. In the Descartes formula, everything is measured from the mirror. We're going to find that with the Newton formula, it's not. So those are the 3 types of images. Remember, 2 of them were real, just magnified either bigger than the object or smaller, and there was 1 virtual image which was bigger. We're going to see the same sort of thing with the converging lens. Does nearly the same set of images. In fact, we might go straight to that for our next video.